When you've been asked to integrate, you've always been asked, quite gently and politely, I hope, to put in plus c. Well, in this lesson, I wanted to try and show you a little bit more what the plus c really means. Let's take a nice simple example. dy by dx is minus x over y. This is telling us the gradient at various points. If I take points where x is 0, then the gradient is always going to be 0. Well, x is 0 anywhere on the y-axis. So we can make a little note to show that by saying the gradient is 0 there, the gradient is 0. It's writing now, that's better. Gradient is 0 at every point on the y-axis. What about the gradient on the x-axis? On the x-axis, y is 0, so your gradient is always infinite. I'm carefully leaving out what happens at the origin. So we have an infinite gradient. If it'll draw for me, it has. So all the way along here, I'm marking little gradient directions. What happens now if I think of any point on the line y equals x? At 1, 1, the gradient is minus 1 over 1, minus 1. At 2, 2, minus 2 over 2, and so on. So anywhere on that line, the gradient is minus 1. So we're getting a little bit of a feel of gradients and curves, and perhaps a little bit more. You might see something just beginning to happen. What about the line y equals minus x? Well, that point is 1 minus 1. 1 minus 1 is minus 1 over minus 1 plus 1. 2 minus 2, minus 2 over minus 2 plus 1. Minus 1, 1, minus minus 1 over 1. Everywhere on this line, you're going to have a gradient of plus 1. Now I can ask the machine to do this for me. If I type into it the equation dy by dx is equal to minus x divided by y, this will find little compass needles, little gradient directions for lots of points on the curve. So if we have this equation dy by dx, you can see that all the points, all the little compass needles that I drew fit well with what's going on here. And we get some picture of what's going on with any curve which satisfies that equation. If we take the curve which goes through this point, at that point it's going up a bit. Then it's probably going a bit further over, a bit further over, a bit further over. You can see the sort of path that the curve would take. And it looks as though it might be going round in a nice, happy circle. Well, once again, I can ask the machine to do this for me. Suppose I start at the point 2, 1. And there. It just follows round and happens to give you a nice circle. This one I hope will be a little bit more slow in its drawing. Starting at minus 1, 1, there it goes, and you can see it traveling through all the little compass needles. Starting at minus 3, 0, round we go. And this is, you're going to see, what we really mean by the plus c. We don't just get one answer. We get lots and lots and lots of different curves which satisfy this differential equation. There it goes. Well, let's do a little bit of algebra now. Let's solve this differential equation. It's not a very difficult one. How do we solve equations? Well, we separate the variables. We put the y with the dy, multiply both sides. We put the dx with the x, which is cheating as usual. So before anyone notices we've cheated, let's put the integral signs in. Now we have integrating a half y squared is minus a half x squared plus c. Let's multiply both sides by 2 and add x squared to each side. Well, 2c is just the same as a c, some constant. Well, we should be able to recognize that equation. X squared plus y squared equals 1 is a circle, radius 1, center of the origin. X squared plus y squared equals 4 is a circle, radius 2, center of the origin. So we are picking up the picture that we've got here. If I start at 1, if I can get my starting point right, there it goes. It went the other way that time. So that's really what we mean by a family of curves. We have a differential equation. It doesn't have a unique solution. Not surprisingly, there is some connection between the curves. In this case, a very strong connection. They're all circles center of the origin. Well, let's have a look at another one. Again, I'm keeping the actual equation quite simple. Let's go and pick up a fresh page and do the same thing. In this case, I'll do 1 or 2. If we are on the x-axis, y is 0. So everywhere along the x-axis, the gradient is 0. Doesn't matter where we are on the x-axis, the gradient is always 0. On the y-axis, x is 0, x is on the bottom, so on the y-axis we always have an infinite gradient. You can see straight away that there's a big difference between the two curves, the last diagram and this one. What happens now if we go on the line, oh, I've lost it, let's come back again. What happens if I go on the line y equals x? If y is equal to x, this is always going to be minus 1. So on the line 1, 1, 2, 2, 3, 3, I will always get a gradient of minus 1. Minus 1 looks like that. Doesn't matter where I am on the line. I'm going roughly on the whole number points, but doesn't have to be. And I can't get that one to work there. What happens if I go now on the line y equals minus x? If y is minus x, minus 1, 1, minus 1 on the bottom, minus 1 on the top, gradient 1. If y is minus x, this must always be plus 1. Plus 1 looks something like that. And we could plot the gradient for all sorts of other points. Let's just look what happens if x becomes large. As x becomes large, if I take y is 1 and x is 4, my gradient is minus a quarter. So it's quite shallow. And if I come out the other side at minus 1, minus 4, or minus 4, minus 1, it's plus a quarter. Quite shallow. Well, that's something we can ask the machine to do again. So let's do that. If I'm in the right place. Yes, there I am. dy by dx is equal to minus y divided by x. That's right. And there it is. So a very, very different picture. You can see that the lines that I put on originally are all doing roughly the right thing. But now you can see the general character of the curves. Very, very different. So let's have a little look at one or two of those. Suppose I start at the point minus 1, 3. Didn't go very far. Let's take the turtle off. That's better. It didn't want to go. Oh, I know what happened. When I started near the place where it was going to disappear, it didn't like it, so it stopped. And it was happier without the turtle on. Let's just see what happens if I put the turtle on again and try at 2, 1. That's better. And if I try down here at 2, minus 1, we're expecting to get something almost the same. There it goes. There it goes. If I come out this side at minus 1, minus 1, off it goes. And you can see you're going to get a lot of curves, all of this sort of shape. This is the family of solutions that you're getting from this differential equation. Come right in close to the origin. And let's have another one in this quarter. So lots and lots of different curves with a similar characteristic. Well, let's have a look at the algebra of this one. If we want to solve this differential equation, we have to divide both sides by y, multiply both sides by dx, and pop in a couple of integral signs. This is all what you did in P4 in your maths A level. Integrating there, you will get log y is equal to minus log x. And I'm going to put my arbitrary constant in as log a. You've now got that log y is log a divided by x. Therefore, y equals a over x. Well, we know what those curves are like. Y equals 1 over x is the rectangular hyperbola which does that. Y equals minus 1 over x would be that one. So what we were looking at on autograph, one curve would be made up from one curve here and one curve here. And same is on this side. Two branches of the same curve. So each time I've set another one off. Each time I set off something, it will only draw one because the gradient becomes infinite and it can't just hop over an infinite line. So it only draws one branch, but there are actually two branches which work. So that one was through 1, 1, this one, or minus 1, this one is much the same. And so these two branches, that and that, those two would both be part of the curve y equals 1 over x.